The purpose of this lesson is to review the decision-making survey you did at the start of the course and to look at some of the lessons that pop out of that experience. A discussion of decision biases often starts with the famous Mueller-Lyer illusion. So if we just glance at this, we probably think that the top line is longer than the bottom line. But if we look more closely and put some guides in, our brain recognizes that in fact the lines are the same length. But if we take the lines away, we're again left with the impression that the top line is longer, even though we know that the lines are the same length. The purpose of the Mueller-Lyer illusion is to show us how easily our brains can be tricked. And it turns out that our brains are easily tricked in a large number of more complex environments. So why is this? Well, no one really knows how the brain works, but one theory posits two brains. We have this system 1 brain, which evolved very early in our life as a species, like other animals, and is fast and impulsive and emotional, and really is shared with a large number of creatures on this planet. But what we have unique to humans and higher primates is also this other system 2, this slower, deliberative, conscious, reflective brain, which we use from time to time. Now, the idea is that most of our thinking is done by system 1, which, like I said, is extremely fast, but it's also a little bit simple, and it's fooled in situations in which our environment is very different from the environment in which this system 1 evolved. So, I think that describes modern life. Our situation now is very different than it was 40 or 50,000 years ago, or even before that. System 2 then does a small amount of our thinking, but it's relatively overtaxed. Now, most of this system 1, system 2 dichotomy arose from cognitive scientists like, for example, Daniel Kahneman and Amos Tversky. And this book here, Thinking Fast and Slow, is a nice little summary by Daniel Kahneman that describes this whole body of work on system 1 and system 2. The problem is we often use system 1 when system 2 would give us a more accurate or better decision. So let's look at the decision-making survey in light of this system 1, system 2 dichotomy. The first question you were asked was, compared to other students in this class, how would you rate your problem-solving abilities? And what we see, and you see here, I've done this quiz with many more people than just your class, we're getting to the thousands now, is that the vast majority of people rate themselves as average, above average, or well above average. Now note that this isn't compare yourself to other people on the street or the people you went to high school with. It's compared to other people who are in formal business education, who got into the school and jumped through the hoops. So this is a bit surprising because it suggests that really the vast majority of people are above average, which isn't what average means. Average means we expect half the people roughly to be above average and half the people to be below average, and only a very small number to be at the extremes, like well above average. So this is the first thing to know about your fellow human beings as decision makers. We'll see through the systems 1, system 2 thinking and the remainder of these slides that we as decision makers are very flawed. But on the other hand, none of us knows it. One thing you probably don't know about the decision-making survey is that there were often two groups of students for certain questions. So in this case, in version 1, which half the class got, it asked about the number of words matching a pattern, 4 blanks followed by the letters ing. The other half of the class got a slightly different version of the question, which was identical, except the pattern for the word was how many words in this novel have the form 4 blanks and then another blank, then the letter N, and then a final blank. And what happens is, if you look at the results, is the version 1, the people given the ing ending, seem to think that was far more likely. One way to see the problem with this result is to draw a Venn diagram of these two sets of words. So if we consider the set of words ending with ing, we get this nice little round circle. But then if we consider the set of words ending with blank and blank, we see that it is a superset. That is, it contains all words that end with ing plus other words. It's a much larger set. So why is it then that people sort of assume that words ending with ing are more common than this much larger superset? Well, this is called the retrievability bias because it comes down to this idea that System 1 is lazy. We can very easily think of words ending with ing, whereas matching the second pattern with more blanks, the blank and blank pattern, requires more cognitive effort. And since it's harder, we sort of make the conclusion that these words must be less common, irrespective of what the Venn diagram tells us. So this is clearly a problem or a bias, is where memories or ideas or thoughts that we can retrieve easily strike us as being more probable. So for example, if I asked you which is more likely, dying in a plane crash or dying of stomach cancer, your answer would depend a lot on whether you've been watching the news or whether you had a friend with cancer. That is, your most recent experiences really colors your assessment of probability. Of course, the only way around this is to get data and actually understand the true probabilities, because we cannot trust our own judgments. This one is an old classic. We're asked about Mark, who is finishing his MBA at a prestigious school, but was one time interested in a career as a musician. And you were asked, given this, is Mark more likely to take a job in management of the arts or investment banking? Now, most people, just over 65%, say management of the arts. But this is almost certainly wrong. Why is this? Well, let's consider the next slide. Here's some data from the Wharton School at the University of Pennsylvania in 2009, which, looking back, was probably one of the worst years in history to get a job in investment banking. But yet, if we look at where the grads from this prestigious MBA program went, we see that within the top 5, most of them are investment banking or investment banking like. But if we scroll down a little bit, we don't see management of the arts. There's very few jobs in management of the arts, which makes it unlikely that anyone, regardless of whether they have an MBA or want to play in a band, is going to take a career in management of the arts. We'll see this again more formally when we look at Bayes' rule, but it is a very persistent bias. People tend not to build in what they know in advance. They don't build in their priors. And in this case, our priors are that very few people get jobs in management of the arts. In this question, you were told that you have 9 almost identical stores, retail stores, something like Aritzia or Old Navy or something like that, and that as a group, these stores were expected to see a 10% increase in sales. So in the base year, you're going to start with 90 million in sales, and you knew in the following year that you're going to have an estimated $99 million in sales for your 10% increase. Now the question was, how is this overall 10% increase going to be distributed between your stores? You see in your base years that some stores are doing better in terms of sales than others. You have your number 1 store and your number 9 store, and there's quite a big difference between them. So the question is, which of the 3 forecasts is most realistic for the next year, given this overall 10% growth? So in forecast A, you simply add 10% to the previous year's sales. So notice that the number 1 store, 10% of $12 million is a good size chunk of change. Whereas down at the bottom, for the store that only had $8 million, 10% of that is only $800,000. So what happens in forecast A? Your number one store is pulling away further and further from your last place store. Now, in forecast B, it's slightly different. You're saying, I don't know anything, therefore I assume all stores are going to be the same. They're going to be the expected value. $99 million divided by 9 stores is an expected value or a mean or an average of $11 million. And the final forecast is kind of a mix of these two. So what happens in the first store is it goes up enough to still be number one, but it doesn't go up 10%. And if you look at the bottom store, number 9, it also goes up, but it goes up more than 10%. So at least in percentage terms, it's pulling a little bit closer to the mean, whereas the top store is still the top store, but on a percentage basis, it also is falling back towards the mean. So these are our 3 forecasts, and which one do you think makes the most sense? It turns out that most people prefer forecast A, in which the top performing store increases its lead over the bottom performing store. Forecast B, which was the mean, didn't attract a whole lot of favor. And then number C, which we call regression to the mean, is sort of in the middle. So what are these 3 different forecasts? Well, they represent very different views on performance. And there's a nice little book out there called The Success Equation by Michael Mauboussin that talks about these 3 different models. In forecast A, what we're really saying is that performance, or success if you like, is due to skill. And that is why the top performing store continues to perform well and pulls away, whereas the bottom performing store continues to be the bottom performing store. The second forecast B, what we're saying in this case is that it's all due to luck. If the performance differences in the base year were due to luck, then of course next year we're just going to reshuffle the dice or reshuffle the cards, and we're going to have a completely different outcome. And we don't know who's going to be the best store or the worst because it's all luck. And item C is the blended model, where it says, success is a mixture of luck and skill. And really one of the reasons we do analytics is to be able to tease these 2 different things out, tease out the signal from the noise, tease out the core performance from the random variations. So now we'll see what that looks like with a little demo. What I do with my students in face-to-face classes is hand them each a nickel, and these nickels either have a blue dot or a red dot on them, and that's determined more or less randomly. And what I ask the students to do is flip their coin 15 times. So they flip it 15 times, and then I want them to record the number of times the colored dot comes up. So on a Canadian nickel, this is the beaver side, and it's going to come up either 0 times or as many as 15 times, or somewhere in the middle. So what their score is in this little exercise is the number of times they flipped a tails, plus 1 point if their coin has a red dot, or 3 points if their coin has a blue dot. So rather than having you flip coins, what we're going to do now is show you a little simulation in Excel. Just to give you a little background on the demonstration, I start with a spreadsheet in which I have about 50 students, and these are listed in the rows 1 to 50. And then I have 15 columns which represent the different flips. Then on the far right, I have the sum of the flips, and then adding in the 1 or the 3 score, I get a total score for each student. Now, the key to this simulation is that underneath every flip is a little formula. And what the formula does is rely on Excel's RAND function, which is a random number generator. Now, what a random number generator does is it generates a uniformly distributed variable on the interval 0 to 1, which means any number between 0 and 1 is equally likely. Now, what this overall function does is it looks at that random variable between 0 and 1, and if it's less than 0.5, it scores a 0. And if the random number is greater than 0.5, it scores a 1, which means every cell in this little flip simulation will either be a 0 or 1, depending on the value of the random number, which changes every time the spreadsheet recalculates. So I've drawn the histogram for the flip at the bottom, and it's pretty straightforward. It's a discrete uniform variable, which means it's either going to take on a value of 0 with 50%, or it's going to take on a value of 1 with 50%, and no other values are possible. That is why it's discrete. So before we look at the Excel simulation to see what happens, it's useful to step back and say what might happen. First of all, we should agree that these two trials, trial 1 and trial 2 of the coin flipping exercise, are identically distributed. That is, using the same coin, the same laws of physics, everything's the same between trial 1 and trial 2. All that should vary is, of course, luck. The second thing is we should recognize that trial 1 and trial 2 are completely independent. That is, your score on trial 1, flipping the coin at least, should have no impact on how you flip the coin in trial 2. Now note that logic isn't universally accepted, especially in places like Las Vegas and so on, where people get very superstitious on the roulette wheel or with dice or with cards about what the next roll or the next spin or the next deal could bring them. They tend not to recognize that these things are really quite luck-driven, maybe not so much with a small deck of cards, but a roulette wheel for sure, dice for sure. The results of the previous roll have no impact on the results of the subsequent roll, even if you're due or if the person has lady luck or whatever. So putting aside gambling superstitions, we should agree in this coin toss that the things are independent. Now, of course, they're not completely independent because each person in the simulation has a skill score of 1 or 3. We should expect that, of course, to influence the outcome, but the actual 15 coin tosses should be just a matter of luck. So what happens now if, say, a person gets a high score? Say they roll a 14. Now, if this were purely skill-based, we would expect in trial 2 that that person would also again get a high score, say another 14. So we can plot that on that point, trial 1 versus trial 2, on a graph. Similarly, we can find another participant who had a relatively low score, and if this were completely skill-based, that is, if that low score was due to that person's lack of coin flipping skill, we'd expect in the second trial for that person to also get a low score like a 5, and we could plot that on the same graph. So what we'd expect then, if this were a skill-based exercise, is some kind of continuity of results. People who scored high in one situation would score high on subsequent trials, and vice versa for people who scored low, and we'd get a very linear relationship between the scorers on trial 1 and the scores on trial 2. And not surprisingly, we actually see this linearity in sports that are skill-based. So for example, in swimming or speed skating, not only do the same people win a lot of gold medals at one Olympics, but they often win multiple gold medals at multiple Olympics. I'm thinking about people like Michael Phelps and Bonnie Blair in speed skating and things like that. So in very highly skilled environments, we do see very consistent results over the trials. Here in this very simple example, we can see in trial 2 that the high score, the person who got a 14, rolled a 9 next time. So that means is their performance actually dropped down a little bit, whereas a person which I picked to have one of the lowest scores actually did slightly better, and they also moved up. Now, in both cases, they rolled a 9 on the second trial. That's a perfect example of regression to the mean. In a very luck-based situation, person who does exceptionally bad, in this case rolls a lot of heads and not many tails, is unlikely to have the same bad luck on the second trial. Similarly, the person who rolled a lot of heads and accumulated a lot of points in this little game is unlikely, because of the luck of flipping coins, is unlikely to have that same luck twice in a row. So not surprisingly, that person also regresses to the mean. And that's what regression to the mean really gets at, is any situation where there's a lot of luck, we're going to see exceptional performers on the next trail go backwards and extremely poor performers move upwards, so that in the end, most of the performance is near the mean, which is what the mean means. So here in our simulation, we have trial 1 and trial 2. And if I hit F9, we see that these recalculate. And now what we do is we plot performance in trial 1, the total, versus the performance in trial 2. And as you can see here, the lines form a bit of a cloud. Now, it is possible to fit a line, a regression line, through these data points. But as you can see from the R-squared, the explained variance near the top, that is not a very high R-squared, which means that line is not a very good description of those data points. But as you see, as we recalculate this and run the simulation over and over again, we see that it really never turns out that trial 1 and trial 2 are highly correlated. Now, of course, the line that we fit to those two different trials is sometimes positively sloped, sometimes negatively sloped, which means we would probably conclude that overall it's got zero slope, which means there's no relationship between performance in trial 1 and performance in trial 2. Here's another example of a question for which there were two different groups with two different versions. In version 1, you were asked to estimate the starting salary for an employee, and you talked to your secretary, and your secretary who said, I know nothing about anything. I know nothing about this, but I'm going to guess $100,000. In version 2, the setup was identical, but in that case, the secretary said, I'm going to guess $40,000. The question is, you know in advance that this information is completely uninformed and it should be irrelevant. Does it impact your own guess of what the salary for this person should be? It turns out that we do tend to anchor on information even if we know the information or the signal is irrelevant. The group that got the anchor of $100,000 from the secretary had a mean guess of geologist salary that was significantly higher than the group that got the $40,000 anchor, almost a $12,000 difference. So the implication here is that if we give people a signal, even if it's irrelevant, people will anchor on that signal when they decide what's appropriate or not appropriate. We see this, for example, at Winners or at stores where they give you a reference number for this item is normally sells for $90 and you're buying it for $60 and you go, wow, that's a deal, even though that $90, that anchor might or might not be accurate. When doing the decision-making quiz, many of you would have noticed that two of the questions were quite similar. The first one is asking you about winning $80 for certain or taking a gamble. The second question is asking you about losing $80 for certain or taking a gamble. Basic gambles like this are the atomic unit of decision making, so it's probably worthwhile to spend a few moments to walk through a decision tree and showing how these work. So we start with a decision in which we either gamble or we don't gamble. And if we don't gamble, then we have certainty. We know our outcome in this case is positive $80. That's great. If we do gamble, then we don't necessarily know our outcome because we have this element of uncertainty. So we add in a chance node to capture this uncertainty. In this case, we know that there's an 85% chance that we're going to win $100 and a 15% chance that we're going to win nothing. Now, to make this decision, we have to be able to compare these two branches coming out of the decision node. One, there's don't gamble $80, but the other one has this chance node. To evaluate this as a decision tree, we need to roll back the chance node. That is, we need to replace it with something we can compare to the sure thing. The standard way to do that is to use the expected value. Here, the expected value is our 0.85 probability of winning $100 plus our 0.15 probability of winning $0. So our expected value of this node is $85. So now, if we compare these two branches emanating out of the decision node, we have $80 for sure, or an expected value of $85. It doesn't mean we win $85, because either we win $100 or $0. But if we played this game over and over and over again, on average, if we gambled, we'd win $85. So the standard thinking with expected value is that, look, this $85 expected value is greater than 80. The rational choice would be to take the top branch, that is, to gamble. Of course, we can reuse our decision tree for the loss version of this gamble simply by replacing the positive signs with negative signs. So here the scenario is that perhaps you get pulled over by the police and you have a decision. You can pay an $80 fine for sure, or you can take your chances and go to court, in which case there's a pretty good chance you're going to pay a higher fine, say $100, and there's a 15% chance that you're going to get off with no fine. So it's identical, but here the logic is different. The expected value of the fine is now $85, and that has to be compared to the sure thing of the negative $80. So here the rational choice is to take the fine. Here we see the results from the actual decision-making survey. On the left, we start with the situation in which the gamble is expressed in terms of winning $80. Now, we said, based on our expected value calculation, that the rational choice was to gamble. But yet, only 34% of respondents selected the gamble. The vast majority decided to go for the sure thing. That is, they'd rather have $80 in their hand instead of gambling for an 85% chance at 100 or a 15% chance at 0. That's fine. But what's really interesting here is the opposite case in which the exact same gamble is expressed in terms of losses. In this case, we saw that the rational course of action was to take the fine, take the sure thing of minus $80, but yet what we see is a majority of respondents gambling. Now, the implications of this, and this has been well studied, is that when decisions are expressed in terms of losses, people are actually risk-seeking, whereas when the gamble is expressed in terms of gains, people tend to be more risk-averse. So that has huge implications for us. If we go to Las Vegas, for example, if we start losing, we might start taking bigger bets. But also when you're pitching projects or new ventures, if you're looking for risk-seeking behavior, just a hint, express the outcomes in terms of losses. Here's another illustration of really the same issue. In this case, you were split into two groups, and the first group got a version of the question in which Canada is facing an influenza problem which will affect 600 people, and you have a choice as a policymaker. If you implement Program A, 400 people will die, and if you implement Program B, which is a gamble, there's some probability that no one will die and a 2/3 probability that 600 people will die. The other half of the group got the exact same question, but instead of using the word die, everything was expressed in terms of the word save. So if Program A is implemented, 600 will be saved. If Program B is implemented, then there's just issues around what proportion will be saved and what the probabilities are. But note that if we start with 600 people, in both these versions, we're really looking at 400 people dying and 200 people being saved. They're really the exact same question. All that varies is the word die versus the word saved. Now, a much easier way to visualize this, of course, is with a decision tree. And here we see the basic issue. If we do not gamble, 400 people die, and since we're talking about 600 people, that implies that 200 people are saved. On the other hand, if we gamble, then the expected value is identical. 400 people die, which means 200 people are saved. Now, based on what we know from the previous slides about risk aversion, risk seeking, and the idea under prospect theory that people feel losses a little bit more acutely than they feel gains, we can sort of have a little theory here. The purely rational case is that a decision maker should be indifferent between gambling and not gambling in this case. But given that we use this word die, and die is a loss, we might expect decision makers to seek out the alternative here, seek out the possibility that zero die, even though the probability is quite small. That would be risk-seeking behavior. On the other hand, when we're talking about saved is expressed as a gain. So really what we expect people to do is avoid the risk and lock down this 200 saved situation. What do we see in the decision-making survey responses? We see exactly what we have come to expect now is risk-seeking in the face of losses when the problem is expressed in terms of people dying, and risk aversion in the face of gains when the problem is expressed in terms of saving people. So just that one word difference between die and save leads to dramatically different policy choices. In this question, what I asked you to do was to read this little vignette about this woman and then rank the likelihood that she belongs to these different groups. Now, I appreciate this was a lot of work, but it was really mostly a distraction. And the distraction was to keep you, hopefully, from noticing a special structure of three of these statements. The first is Linda is active in the feminist movement. Linda is a bank teller. And the third one is a conjunction of the first two. Linda's a bank teller who is also active in the feminist movement. Now, we can draw a Venn diagram showing the probability of each one of these statements. We start with the two major statements that Linda is active in the feminist movement and that Linda is a bank teller, and then we focus in on the intersection of these two sets, which is where Linda is a bank teller who happens to be active in the feminist movement. And when we display the information this way, it should be clear that this intersection cannot be larger than either one of the other two sets. That is, if you are a feminist bank teller, then you are also a feminist. What we see here in practice, though, in spite of the rules of logic and set theory, is that some people think this intersection area is larger than the two components. That is, some people, in fact, a vast majority, 82%, seem to think that the intersection, that she's a bank teller feminist, sounded more likely than either one of the other two. And in 15% of the cases, respondents rated the intersection as being more likely than both the other two. So this is clearly impossible. And the question, why is this? Well, we could call this one the narrative fallacy. By telling the story about Linda that's full of detail, it's very much like when we told the story about Mark, the guitarist with the MBA. If the story stuck together, we created a vision in our mind of what this person was. And in this case, the intersection seemed to correspond closer to Linda than the much less detailed, very simple, she's a bank teller or she's a feminist cases. So the narrative fallacy draws us into making logical errors in probability estimation. In this set of questions, you were given an unknown quantity and asked to provide a couple of things: a best estimate of the unknown quantity, and then a confidence interval around your guess. So, for example, the first question was about the age of Dr. Martin Luther King Jr. when he died. So maybe you would have guessed that he was about 50 years old when he died. Of course, you weren't expected to know the answer to any of these questions, and you certainly were not expected to go off and Google them. But say if you guessed something like 50, the next part of the question was to provide a confidence interval such that you were 95% sure that the true value, the actual age of Martin Luther King when he died, would fall within your confidence interval. So, for example, you might have said, well, I'm pretty sure that he was older than 40, but less than, say, 70. And then when we look at the actual value, we see that in this case, you would be overconfident with this guess. That is, his actual age at death was 39, and if your lower bound was 40, then the actual value falls outside your confidence intervals. Now notice there was no reason not to answer all these questions with minus infinity, positive infinity. That is, there was no penalty for being under specific when you answered these questions, but very few people gave me negative infinity, positive infinity. Most people gave very specific, in fact, absurdly specific confidence intervals. There's an old saying about some people being often wrong but seldom in doubt. But these results suggest that the problem is more widespread. For each of these questions, a significant number, and in some cases a majority of people, gave a confidence interval that was too tight, and the actual answer was outside of their confidence interval. So it's very important to know this when you're in meetings and dealing with other decision makers, that as humans, we have a tendency to be over precise and overconfident when we give answers. This is a very old and famous question and turns out to have a lot in common with Mark, the guitar playing MBA student. The setup is that there's some cabs in this town, and the majority of these cabs are green, and the remaining 15% of the cabs are blue. And then there's some kind of accident, and a witness steps forward and says, I saw the accident, I saw the hit and run accident, and the offending cab was blue. But then they do something quite unique and interesting. They test the reliability of this witness. So you can imagine them being out on some foggy night, and the sheriff says, okay, send around a blue cab. And when the blue cab goes around the corner past the witness, they ask the witness, what color is that cab? And 80% of the time in this case, the witness would say blue. That is, the witness would correctly identify the color of the cab. And 20% of the time, given that they knew the cab was blue, the witness might say, oh, it's green, and vice versa. So they have some data now on the reliability of the witness. And the question is, okay, given that the witness said the cab was blue, what's the probability that the actual cab was blue? Now, most people get a little bit annoyed by this question, and they say, well, look, your witness is 80% reliable, and your witness said it's a blue cab, therefore, the probability of the cab being blue is clearly 80%. But what this misses is the base rate, these a priori probabilities that in this town, most of the cabs are green. That turns out to matter. Now, we'll see more on this so-called Bayesian updating when we get to the lessons on that topic, but here's the basic intuition. Let's assume we take 100 cabs and run them past our witness. But let's also assume that those 100 cabs are colored in proportion to the population, that is, to the distribution of colors in this little town. So the key issue here is that our witness is not perfect. Our witness is going to make some mistakes. So the first type of mistake the witness is going to make is a false positive. That is, the witness is going to identify the cab as being blue when it's actually green. Now, because 85 of the cabs in this sample are green, 85 times the 20% error rate is 17, and that turns out to be quite a large number. Then we have what are called the true positives. That's when the witness says the car is blue when it's actually blue. And given that the witness is fairly good, fairly reliable at 80% reliability, 0.8 times the 15 blue cabs means the witness correctly identifies 12 of the 15. Now, the other 3 are false negatives. He actually sees these blue cabs as green because, remember, the witness is only 80% accurate. What we're really interested in, though, is the situation in which the witness says the cab is blue. So this happened a grand total of 29 times. Unfortunately, 17 of those times were false positives, and only 12 of them were true positives. So this overall success rate is 12 over 29 is about 41%. So about 41% of the time when the witness says it's a blue cab, it's actually a blue cab, and actually the majority of the time, 59% of the time, it's a green cab. This entire thing is driven by the fact that most of the cabs are green. For this last question, you were split again into 2 groups, and the first group got a version of the problem in which you're standing near a railroad track and there's a runaway trolley, and if you do nothing, the trolley is going to go through and kill 5 workers. Now you assume these workers have ear protection on and can't see the train coming or whatever. However, there's a switch there, and if you pull the switch, you can divert the runaway trolley. It will go down a different track and kill only 1 person. So it's a very straightforward moral dilemma. Do you do nothing and let 5 people die, or do you do something, pull a switch in this case, and kill 1 person? Now, the other half of the class got a different version of the question. Although it's quite similar, the setup's a bit different. There's the same runaway trolley, but you're up on a bridge and you notice an enormous fat man looking at the runaway trolley, and you reason that if you can just lean into the fat man and push him over the bridge, he will land on the track in front of the trolley and derail it. And by doing so, we'll save the 5 workers who don't see the runaway trolley coming. But of course, you will almost certainly kill the fat man. So the question is, do you push the fat man? Now, before we continue, I should make it pretty clear that this isn't my question. This is a pretty well-studied problem. In fact, it's a very well-studied problem. And in fact, this last book I do recommend, and if you look on the cover, there is the trolley. So this is a well-known problem, and it gets into this issue of how people make decisions given a moral dimension. So the question here is, given that both problems involve killing 1 person to save 5 people, does the setup, does the switch matter? And it turns out it absolutely matters. In the throw the switch version, the vast majority would act to save the 5. However, in the push the fat man version, an equally large majority would not push the fat man. So who knows why this is? There's some speculation about the physical contact with the fat man. There's different versions of this problem in which the fat man is dressed as, say, a Nazi officer, or the fat man is the owner of the railroad and is therefore somehow complicit in the accident. And like I said, this is a well-studied problem with lots of permutations and combinations. But the important thing for us is to realize that a moral dimension can very much impact the way people formulate, think about, and then make decisions.